In today's lesson, we're going to begin to learn about the chemistry of gases. Specifically, I'm going to talk about temperature and pressure. We're going to look at mixtures of gases. We'll talk about partial pressures. And then I'll introduce the kinetic molecular theory, which is an understanding of how temperature works and how collision theory works. And then we'll discuss the gas laws, including Boyle's law, Charles' law, Avogadro's law, Gay-Lussac's law, the combined gas law, and the ideal gas law. And then at the end of the lesson, I'll have a bunch of practice problems that I'll work through, and you can stick around for that if you'd like. To begin with, let's look at this representation and ask the question, what is it representing? Well, I have some type of compound or molecule here that has two different atoms because I would assume that the red and the blue are different atoms here. And in this case, these molecules are freely moving about this container, which looks like it's compressible. There's a piston here at the top. So in this sense, this is unlike the other materials that we've been working with solids or liquids, in that there is whatever volume available that substance occupies. So this is a representation of a gas. And is it a mixture or a compound or an element? Well, if we remember our difference between a compound and an element, a compound has to have two different atoms and an element has the same atom. So this is definitely not an element. And then for it to be a mixture, there has to be two different substances, but all of these compounds here represent the same substance. So here we have gaseous compound. And we'll talk about gaseous mixtures in a little bit, but this is kind of the representation we're going to start using here. And when you think of a gas, what do you think of? This is something I like to ask students because a lot of times we might be thinking of some type of invisible substance. And in general, that is what most gases are. They're things that we can't observe with our eyes. But we also might think of something that's smoky white, like fog, or something that's darkly colored, like a dangerous gas that happens to be colored. But it could also be something that's light or something that's heavier. So there's different densities of gases. And something, it might be something that's inert or harmless, or it could be something that's essential for life. So when we think about the air that we breathe, there's the inert nitrogen that's present, and then there's the essential oxygen component. Something that's toxic and suffocating. Well, it's the summertime here in Boise, and we start to get in a lot of smoke this time of year, and there's a lot of particulates in the air, in addition to the gases that we normally think of, and those can be quite dangerous when they're present in higher amounts. And one of the interesting things to me when I study the history of chemistry is that the study of gases was largely ignored for most of the history of science. And I think it had to do a lot with the difficulty in separating out the different gases that are present and being able to observe something that is otherwise colorless and invisible to the senses. But nowadays, I think it's pretty obvious that multiple gases exist and that most substances can, under different conditions, higher temperature or lower pressure conditions, transition into a gas at some point. And the first discoveries of gases, they only occurred around the 1600s. And this was with the advent of different vacuums. And a vacuum is the ability to remove most of the gas from a container. And with the invention of the vacuum pump by Otto van Guericke and the improved design by Robert Hooke, they were able to isolate out gases, create areas that were evacuated from gases and then fill those and then study those pure substances, those pure gases. And we're going to be looking at some gases today, and you'll probably recognize that most of them are very simple compounds. So most of the simplest compounds are gases. Let's look at a video of a type of gas prepared from dry ice. And in the last videos I showed you, I don't think the volume transferred over. So I'm going to make sure I have the subtitles here. This is a demonstration by Peter Vother. He's a British chemist, and he does a lot of these really fun demonstrations. So if you like this, you might enjoy some of his other. Okay, so this tank here is filled with carbon dioxide, and at the bottom of it, notice that there's like this white substance down here. This would be solid carbon dioxide, also known as dry ice. So they put a bunch of dry ice at the bottom of this container and just let it filled up with the gas as the dry ice sublimated into gas. And then there's a crucible here. He's going to um, try to burn some petrol, some gasoline. Okay, so gasoline. We'll talk about what type of chemical reaction this is, but that was instantly put out when they put CO2 in there. Okay, here's a big strip of magnesium. Okay, so that's a pretty cool demonstration, I think, to kind of show the mystery of gases. And let's break down what exactly was going on here. So, petroleum or gasoline is a type of hydrocarbon, and without being too specific, let's just write it as CnHn. And the reaction that was occurring when it's burning is a combustion reaction. So that needs oxygen to thrive, and in the result of that, you'll get carbon dioxide and water vapor. So the issue here is if you have a container of CO2, there's not going to be very much oxygen present anymore. So if we try this same thing without oxygen, just write it this way, CnHn plus CO2, we don't get any reaction because there's no oxygen present. But if I take burning magnesium, so we'll start with magnesium, and we put it in the presence of oxygen, we do get a reaction. So we get magnesium oxide. But we can also burn magnesium in the presence of carbon dioxide. So this is kind of an interesting thing here. The magnesium is a really good reducing agent, so it can be easily oxidized. It can strip the oxygens from the carbon dioxide, and what will end up happening here is we'll form magnesium oxide just the same, but there will be excess carbon. So if we go back and look at the end of his video, if we look at the bottom of the container, there'll be the white substance, that's the magnesium oxide, and then there'll be all this black soot, that's the carbon here in this reaction. So Carbon dioxide can react with different materials. It just can't react with petroleum. All right, so to continue on with the lesson, let's kind of look at some of the different properties that gases have, because they are a little bit different than solids and liquids. So a lot of times we look at gases over a variety of temperatures. So we'll want to think about what temperature means. We'll want to think about the property of pressure, because gases are easily compressed and expanded. The density of gases can vary considerably, so that's something we should think about. The speed of gases can change a lot as well, so that's an interesting property we can measure. The volume of a gas is something we'll need, as well as the amount of a gas, meaning how many moles there are of it. And we can relate a lot of these properties with different laws, and we'll get to that by the end of this lesson. So I like to think about temperature first, because it's something that we can understand as, just a kind of as a human perception. So when I think about the temperature being warm, that's always in comparison to our body. So if the temperature is warm relative to our body temperature, we can perceive it as warm. If I put my hand in cold water, the water itself is cool compared to my body, and that's how we can determine that it's cold. But scientifically, we look at temperature a little bit differently. We think about it as a measure of the motion of the particles. So how quickly are the particles moving, whether they're liquid or gas, determines their temperature. So a colder temperature in a room has less motion of the particles in the air than a hotter room. And we can make measurements using thermometers of temperature, which measures the degrees of hotness of that material. So the most common device is the glass thermometer. The glass thermometer consists of a glass tube filled with mercury or some liquid such as ethanol that can expand at a constant rate. And that acts as the working fluid. And whenever that substance comes into contact with a warmer or a cooler substance, the volume will contract or expand, and there'll be different markings on the thermometer that allow us to determine what temperature is. But you first obviously need to calibrate the thermometer so you know exactly what it is at a specific temperature. And a lot of the early temperature scales were calibrated based off of different set points. So the Fahrenheit scale was the first that was proposed in 1724. Before then, I'm sure there was other types of temperature scales, but this is the most commonly used temperature scale here in the United States. And it was originally defined as 0 degrees as the temperature at which a mixture of ice water and ammonium chloride freezes. And then 32 degrees would be the temperature at which pure water is to freeze. And 96 degrees Fahrenheit is about what the body temperature is. The Celsius centigrade scale was proposed about 18 years later by Anders Celsius, and he defined it differently. He said that 0 degrees Celsius is the melting point of ice, and 100 degrees Celsius is the boiling point of water. So 0 degrees Celsius and 32 degrees Fahrenheit are equivalent on these two scales, but because the set point of 100 degrees Celsius is much different than the body temperature is close to 37 degrees Celsius, we can't relate the Fahrenheit scale and the Celsius scale using a linear equation because they're offset by a lot. And then there was another scale that was proposed by Lord Kelvin, and I don't have the year here, but he proposed a different set point. He suggested that the 0 scale on his on the temperature scale should be when there is 0 motion of particles, and he set the absolute 0 to be negative 273.15 degrees Celsius. And I think it would be interesting to learn about how he came up with that number, I don't actually know. I'm sure he extrapolated based off of different data, and you can do that. So when working with gases, we'll use the Kelvin scale because it's based on the absolute scale, where 0 refers to no molecular motion. And there may still be some vibrations at 0 degrees Kelvin, but that's essentially when the molecular motion, the translational motion of particles is absent. And we'll need to convert everything that's in Fahrenheit and Celsius to Kelvin. So here are 6 conversion factors. I believe they're all correct. So say, for example, we want to convert from Celsius to Fahrenheit. We'll use this first one. The opposite would be the next one. And then this one will be pretty important. So if we want to know what the Kelvin temperature is, we just add 273.15 to the Celsius scale. So you can see that the Kelvin and the Celsius degrees are equivalent. So 100 degrees difference in Celsius is the same as 100 degrees change in Kelvin. However, for Fahrenheit, it's very different here. And then if you wanted to convert directly from Kelvin to Fahrenheit, you can combine these two equations to get this one and the opposite here. All right, so let's practice a couple of these just real simply. I don't know why it says 14. That should be question 1. That's fine. I'll leave it. Convert negative 115.1 degrees Celsius to Kelvin. Well, we'll just find the equation that we need. So that would be this one right here. And like I said, we'll just add 273.15 to each of the Celsius temperatures. So. One thing to remember here is that because we're using the rule of addition for significant figures, we're only going to be significant to 1 decimal place here, so 158.1. And because it's in Kelvin, we're not going to write the degree symbol. We'll just write a capital K. And anytime you find a Kelvin temperature, it has to be greater than 0. So that's a good way to check that you got it right. So we can have negative temperatures, but only if they're negative Celsius and negative Fahrenheit. And oh, this is kind of interesting. The most negative Fahrenheit is negative 459 and negative 273. So Fahrenheit and Celsius. If we want to convert the opposite direction, we're just going to subtract 273 here. $163.0. That would be very hot temperature. Okay. Now the next one, this is common if you're going between Europe and the United States a lot, is having to convert between Celsius and Fahrenheit. And you see a weather report that says it's 20 degrees Celsius. You want to know if it's going to be warm out, if you should wear a jacket that day. So let's figure out how to convert between the two. We'll start with this first conversion factor. We'll need to multiply the Celsius temperature by 9/5, which is 1.8, and then we'll add 32. So multiply this by 9/5, and then add 32. All right, so 20 and 5, that reduces to 4. 4 times 9 is 36, plus 32. That gives us 68 degrees Fahrenheit. So that's a pretty nice day out. Might not need a jacket unless it's in the evening. So that's, we're just going to introduce each of these properties one by one. So that was temperature. Now let's look at pressure. And pressure is simply the amount of force that's applied over an area. So if I have a small area that I'm applying a force over, I'll have a large pressure, versus if I take that same amount of force and I apply it over a larger area. So it's important to think about pressure in this sense of as a force over an area. And my initial quote here at the beginning is, "We live submerged at the bottom of an ocean of elementary air, which is known by incontestable experiments to have weight." It's really strange that we don't notice that there's a whole bunch of air around us that's pushing down on us all the time. It's just because our body is so used to it. But if we go under the water, we'll notice the weight of the water being put on us pretty quickly, and we can only dive to a certain depth before it gets uncomfortable, and we need to regulate the pressure. So there are a lot of different pressures that are used, and I have this long conversion factor here. So all of these are equivalent to each other. If I say 1 atmosphere, that's what I mean by standard pressure. And if I say 760 millimeters, that's mm is millimeters, and then Hg is mercury. So if I say 760 millimeters of mercury, that's the same as 1 atmosphere. So all these are equivalent to each other. Sometimes people say the standard atmosphere is 1 bar. I'm going to use it as 1 atmosphere for this class. And then there's torr, that's equivalent to millimeters of mercury. That's named after Torricelli, who designed the first barometer. And then there's the kilopascal, as well as the pascal, which would be, you'd multiply this by 1,000. And then there's PSI, which stands for pounds per square inch. That's used a lot when we're working with pressures in cylinders and in tires. And then we could also, of course, do inches of mercury. And then there's the bar, which 1 bar is pretty similar to 1 atmosphere. Now, although the official SI unit is the pascal, this is a very small unit. So that's defined as 1 Newton per square meter. So if you're going to do everything in SI units, you do want to use the pascal. Let me add that to my list here. 101. So that you need 101,325 pascals to equal 1 atmosphere. So it's kind of a strange unit. And I kind of touched on this already. Now, you can read through this. This makes sense. If I have, the reason I can put a nail through a board is when the impact of the hammer, the hammer's weight hits the nail, it's going to drive the nail into the board, because there's a large pressure from the bottom of the nail transmitted through the force of the hammer over a very small area. So the pressure is really, really great, and so it just goes right through the board. But if I do the same thing with my hand isn't going to go through the table. That's because the palm of my hand is much greater, and I can't really get a pinprick on my hand. So what else do we want to think about? So we can measure the subtle differences in air pressure using a barometer. And when we watch a weather report and we hear about a low pressure system or high pressure system coming in, those are these subtle differences in air pressure. The first barometer was invented in 1643 by Evangelista Torricelli in Italy, after he was interpreting the results of Gasparo Berti's experiment. So Gasparo Berti was trying to understand how siphoning water could work, which is how you can take waters water from a low area and move it up to a higher area using the property of uh, essentially capillary action, where the water will move up through a straw through capillary action through the intermolecular forces of being attracted, because water is a polar molecule. So what he did is he wanted to study this in detail, and he took a long tube that was plugged on one end. Actually, no, it was no. Yeah, so he had a long tube, and it was covered on one end, and then he basically stands the tube into a basin of water. So it's covered at the top here, and so all of this was filled with water at the top, and so it's filled all the way up here, and on this very bottom it's closed. And so then he puts the basin, he puts the tube into the basin of water here at the bottom, and he notices that some of the water starts to fall into the basin and fill it up. However, only part of the water flows out, and then it just stays at a level of 10.3 meters. So why does the water not completely flow out of the tube, but a lot of it stay in the tube at this level of 10.3 meters or 34 feet? Well, it's kind of an interesting thing to think about, and I think we really ought to consider what's going on here. So the basin here is open to the atmosphere, and the atmosphere itself, like I said, is pushing down on us all the time. So there is this pressure due to the atmosphere being pressed down. And then you have the weight of the water pushing down here as well. So the pressure due to the water. And those two cancel each other out at 10.3 meters. And so you can indirectly measure the pressure of the atmosphere through having a long tube of water. Now, this type of a setup might work well in a town square here, but it didn't work that great, in like a classroom setting, or having a barometer that's easily available. So Torricelli, working with I believe Galileo, was working with this mystery substance known as mercury. Mercury was you didn't really want to be telling people you're working with mercury at that time. He was kind of doing some of these experiments in secret. So it was originally thought that air didn't have any weight at all. And this was kind of a big deal, right? So trying to prove that air had weight was something that most people didn't want to agree on. So Galileo himself had accepted that air was weightless, and he accepted this as a simple truth. So Torricelli, he questioned this assumption and proposed that air did have weight. And he set it up, his experiment here, instead of with water, but now with mercury. And so there's mercury here in this dish, so liquid. It's a liquid, and then he filled the tube here with mercury as well. And the height of the tube now is 760 millimeters of mercury, when it was 1 atmosphere of pressure outside. So Torricelli recreated Bertie's experiment, but now it was 14 times using mercury, which is 14 times denser than water. Now you only needed a tube that was roughly 1 meter tall. So 800 millimeters was needed. So the mercury barometer was a huge deal, because not only did it tell us that air had weight, but also, interestingly, it created a region up here, which was a vacuum. So there's actually a vacuum that was created in the process. And what was the year of this? This was 1643. So this was right around the time that vacuums were being discovered. And this here was, again, another like truth that people thought that vacuums couldn't exist, because if there was a empty space here, something should fill it, right? But this tube here was initially filled with mercury, so nothing is able to diffuse through the mercury to fill that space. So there's actually literally nothing there. So you could create a vacuum with mercury, which is another cool discovery. All right, so here we recognize that 1 millimeter of mercury is known as the torr, and the pressure is quoted as the level of the mercury's height in the vertical column, because that's when those two pressures, the atmospheric pressure and the pressure due to the weight of the mercury, cancel each other out. So he also noticed that the height of the mercury in the barometer would change from day to day, and he concluded that this was due to the change in the pressure in the atmosphere. So this is a really interesting intuition that he had, and he would recognize that when low pressure occurred, there was usually a storm the next day. Here's that quote here from the beginning. And then I mentioned this already. Okay, so let's practice a few more things here. We did this already. So let's convert a pressure of 37.4 psi to atmospheres using these conversion factors. So we can just use dimensional analysis for all of this. There's 14.7 psi in 1 atmosphere. So we just have to divide the two as such. All right, so 2.54. What pressure in millimeters of mercury is equivalent to 1.350 atmospheres? So we'll start with the known value. And then 1 atmosphere, we're always going to start down here with 1, and then 760. So we will have to do a lot of conversion factors for pressure, so that's why I'm working through these with you. So 1,026. Okay, so here's an example of a manometer. A manometer is something where you can use, where you can find the pressure of a gas. So instead of it being empty on one end, we actually have a gas contained in this other end here. We initially have it closed, and then we fill the manometer with a substance like mercury, and then we leave one end of it open to the atmosphere. And then we open the gas, and at some point there will be one end will be lower, and then the other end will be higher, and it could be the opposite direction, or they could be equivalent. And the difference here in the heights of in the height of the tube is equivalent to the difference in the pressure here. So we have the pressure from the gas, and then we have the pressure from the atmosphere. And the difference in those pressures is equivalent to this height difference. So this equals the difference in the pressures. So based on the image, how does the pressure of the gas in the manometer compare to the pressure of the atmosphere? Well, if the pressure of the gas is higher, it's going to press down more and lead to it looking like this in this situation. So here we have a gas pressure that is higher than the atmospheric pressure because its pressure is pushing down more. We can also find what the pressure of the atmosphere is, or what the pressure of the gas is. So here we have that it's 760 millimeters of mercury. That's the atmospheric pressure. And then we want to know what the pressure of the gas is. Well, the difference here shows us that the pressure of the gas is more by 264 millimeters. And so this is millimeters of mercury again, because this substance is mercury. So what we're going to say is that the pressure of the gas is equal to the sum of the two. So the atmospheric pressure plus the difference in the pressures. Okay. Now, what about the situation where we have a mixture of gases? Okay, well, we know that most gases don't exist as pure substances, but they exist rather as mixtures anyways. So why not discuss what a gas mixture is? So one thing that we have to do is we have to erase all this, kind of talk it through slowly here. If we want to consider a mixture of gases, we need to convert the amounts of the gases into moles, and we want to compare how many moles of the one gas there is to the other gas. And we do this through the use of a mole fraction. So if I have a gas mixture composed of 15 grams of hydrogen and 15 grams of oxygen, it's not going to be a one-to-one mixture because oxygen is much heavier. So by moles, there's actually a lot more moles of hydrogen. So the mole fraction of hydrogen, that's going to be represented by this Greek letter chi, is the moles of hydrogen divided by the total moles of the gas. So we have, I can just kind of undo what I had here. So if we take 7.44 moles of hydrogen and divide it by the moles of the sum of the two, we'll get this number, which is 0.941. So it's not a percentage, it's a fraction. So if we wanted to convert it into a percentage, that would mean 94.1% of the gas in that sample is hydrogen. And then likewise, we can do the same thing with oxygen and find that only 5.9% or 0.059 mole fraction is oxygen. Now, what we should notice that since it's just made up of these two, the sum of the mole fractions should equal equal 1 exactly, because there's only two gases present. So you could, instead of doing the second part, you could just subtract 1 from this answer to find the mole fraction. Now, calculating mole fraction is really useful for determining the individual gases' contributions to the total pressure, because we're going to make this really nice, simple assumption that the pressure contribution is proportional to the amount of each of the gases that is present in there. So if I have a total pressure of a gas sample and it's 3 atmospheres, the partial pressure of the individual gases can be found by taking the mole fraction of each of those gases and multiplying it by the total pressure. This assumption is known as Dalton's law of partial pressures. This is the same Dalton that came up with the postulates of the atom. And so he did a lot of studies on gases and found that the sum of the partial pressures of the gases is equal to the mole fraction times the total pressure of the gases. And so we'll always find that the sum is equal to the total parity. And you can extend this to more than 2 gases. You could have 3 or more gases in a sample. So the total moles of the gas the total moles of the gas is equal to the moles of each gas component, and then the mole fractions of all the gas components should equal 1, and then the partial pressures of each of the gas components will equal the total pressure. If we have one particular gas that we want to look at, we can summarize the rules as such. We can take the partial pressure of that sample A and divide it by the total pressure, and we'll find that the moles of A is divided by the total moles of the sample. And this is just that relationship that pressure and amount are directly proportional. So if I increase the pressure of a sample, then I must have increased the amount of that sample, given that the temperature and the volume didn't change. And so we can also represent this as NA over N total as the mole fraction of A. And then we could say that the pressure of A is equal to its mole fraction times the total pressure. So this relationship right here is super useful if we already know the total pressure of a sample, which is really easy to measure. And we are able to calculate the mole fraction because we know how much that we started with. And a lot of times it's important to figure out what the partial pressure is. But we can also figure out the partial pressures in other ways too. So let's look at an interesting experiment here that's used a lot in chemistry to collect samples of gases. So if I have a reactive metal and I dissolve it in an acid, for example, I can produce hydrogen gas. And I can collect that hydrogen gas if I have a setup like this. So let's take a look at this video. This is not a reactive metal here, but instead potassium chlorate. So if I have potassium chlorate, I can react this with the oxygen that's in this tube. Or sorry, not the oxygen that's in this tube. Sorry, let me start over. Potassium chlorate, when heated, will decompose into potassium chloride and oxygen gas. Okay, so we'll produce a solid and a gas. Well, if we heat this and produce this, only the gas is going to be able to move through this tube. And so if you invert a container and you place it in water, you can collect a gas over water. So this is a really useful way to collect a gas. And right now, this tube is filled completely with water. So as this gets heated, you'll note that bubbles will come here and displace the water from this tube, and then the container's volume will increase here because that water was being displaced by the gas. And then if you're careful and you remove this tube, you can find your sample there. Now, what is going on here at the molecular level? Well, we've collected that gas there. We've collected the oxygen above the water sample, but that doesn't mean that only the oxygen is present in that gas sample. There's actually small water molecules that are also present here. And so when we look at the total pressure is going to be equal to the partial pressure of the oxygen plus any component of water vapor that is present there. And no matter what temperature there is, there's always going to be some component of water that's in the gas phase. At low temperatures, it's not going to be very much, but as we get closer and closer to the boiling point of a substance, the amount of water vapor increases, and this partial pressure component becomes very significant. We can figure out the partial pressure of the oxygen component by taking the total pressure that's measured and subtracting the partial pressure of water that's there. So we don't get quite a um, we don't get a completely pure sample of oxygen, but it's quite pure. So let's take a look at how to do some of these calculations. So let's consider where I have my original idea here. I have a metal, reactive metal, and I have hydrochloric acid. And I dissolve the metal in the hydrochloric. What will happen is we'll produce zinc chloride, which is aqueous and will stay here in the test tube. But then the hydrogen gas will get bubbled through, and you'll end up collecting here the hydrogen, which are these white elements here, above the water. So what my question here is, what is the partial pressure of hydrogen if the total pressure is 0.985 atmospheres? And we find that total pressure by just measuring using a barometer in the classroom. And we can find the temperature of their water by using a thermometer, and we find it's 20 degrees Celsius. So we got to also figure out what the contribution is here from the water vapor. So here's a water vapor pressure table, and we'll see that at very low temperatures the pressure is very, very small, and then at 100 degrees Celsius the pressure is equivalent to 1 atmosphere. So at a substance's boiling point, its partial pressure is going to be equal to 1 atmosphere. So that means it easily evaporates. It's going to undergo that phase transition very easily. So here we have 20 degrees Celsius, and the partial pressure of the water is going to be 17.5. So if we want to figure out what the partial pressure of hydrogen is, we need to take the water vapor into consideration, and this will equal the total pressure. The total pressure is 0.985 atmospheres here. And this is in millimeters of mercury. So what we're going to need to do is convert millimeters of mercury to atmospheres so that we have the same pressure units. And so if I substitute in here this pressure that we've just found, then I can subtract that from both sides and find that the pressure of the hydrogen is just slightly less than the atmospheric pressure. Cool. So that's mostly what we need to know here about partial pressures, as well as this relationship that can be quite helpful. Okay, so the next thing I want to talk about is volumes of gases. And this is something I almost always want to introduce earlier, just because it's such a useful concept to understand. So first off, gases always take the shape of the container that they are put into. So they can be easily compressed, easily expanded. And one remarkable thing about gases is that equal amounts of gases, regardless of their molar mass, take up the same amount of space. So when I say equal amounts of gases, I mean equal moles of gases. regardless of their molar mass, will take up the same amount of space. And that means that 1 mole of hydrogen takes up the same volume as 1 mole of oxygen. I think I mentioned this in a previous lesson. So this is the law of Avogadro, and this is the same Avogadro that came that we use the 1 mole equals 6.022 times 10 to the 23rd entities. So Avogadro experimentally proved this and used this law to help determine the correct molar masses of the simplest gases. So if we say, for example, that we combine hydrogen and oxygen together, we know when we take those gases and we ignite them, we're going to get water vapor. And this experiment here, for the longest time, a lot of scientists thought that hydrogen and oxygen were just HO, and that the formula for water was HO. So the problem with that, though, was, say, for example, if we balance this reaction correctly, we see that 2 moles of hydrogen need to react with 1 mole of oxygen to get 2 moles of water. This here didn't show equal volumes reacting. So for a long time, people maybe didn't think that you needed to have equal amounts of gases, or that equal amounts of gases took up the same amount of space. So he was able to show essentially this, and prove that hydrogen and oxygen are diatomic, and that water has the formula of H2O. So one useful conversion is that under standard temperature, which is going to be 1 atmosphere and 273 Kelvin. So under standard temperature and standard pressure, STP, that 1 mole of a gas occupies 22.4 liters, which is about the size of a beach ball. So if you have 1 mole of a hydrogen sample, it occupies about a beach ball size volume. And then if we use the more current standard based on 1 bar of pressure instead of 1 atmosphere, the volume would be just slightly larger. So here's kind of like an explanation I wrote up here of why some chemists didn't accept this. Well, they thought hydrogen's smaller than oxygen, so why should it take up less space? But the idea is that the gas phase of matter is one in which the particles are completely separated from each other, and they're free of those intermolecular forces, at least at high temperature and low pressure conditions. But these particles are very, very far from each other, and so they shouldn't interact very much. And therefore, the volume of hydrogen versus oxygen, its actual molecular volume, doesn't really matter. And they occupy the same volume of a gas. So let's talk about this in the framework of kinetic molecular theory, which is how we understand the behavior of gases in terms of their motion and interactions with other molecules. It provides a microscopic explanation or molecular explanation for the macroscopic properties of gases that we can easily measure, such as pressure and temperature and volume. And it's based on these key postulates. The first thing that we should keep in mind is that when gas molecules move, they're moving constantly and they're moving randomly. So this asserts that when we have gas molecules, they're always going to be moving with also a variety of speeds. Their motion should be in a straight line, and they only change direction when they collide with another molecule or with the walls of their container. We should also consider that the volume of individual gas molecules is negligible compared to the volume of the container. This means that the total volume occupied by all the gas molecules in a container is going to be much, much less than the volume of the container itself. And this is why we can easily compress a gas. The third postulate is that no intermolecular forces will be present in an ideal gas. This theory assumes that these forces of attraction or repulsion won't be present, and we'll correct that in the next lesson, because in reality these forces do exist, but the ideal gas approximation is going to be very good when it's a high temperature and low pressure condition. The fourth postulate is that whenever these collisions occur, they're elastic, meaning there's no net loss of kinetic energy, that the particle will hit another particle and then it will just go in another direction. It'll keep its momentum. So the total kinetic energy of the molecules will remain constant. And then the fifth postulate is that, and this one's, I think, the most important, is that the average kinetic energy of gas molecules is proportional to the absolute temperature. So the absolute temperature is the temperature in Kelvin. So whenever we're measuring temperature, we're measuring the kinetic energy of the gas molecules when we think of temperature in terms of Kelvin. So this is, and then kinetic energy, that's also a measure of the speed and the mass of the particles, because kinetic energy is 1/2 times the mass times the velocity squared. So we're also thinking about, so we can also kind of relate the temperature to the mass and the volume, the velocity of the particles, and we'll get into that, I think, in the next lesson as well. So it implies that as the temperature increases, the average speed and the average kinetic energy of the gas molecules will increase as well. All right, let's look at a couple different examples. If I have a rigid container, how does the pressure change when the temperature increases? So if I have a rigid container, how will the pressure change when the temperature increases? Well, if I increase the temperature, this will give more kinetic energy to the gas particles. And I'm going to treat them as particles. I mean, they might be molecules. I'll just say the word particles. And then those particles then will have more collisions. And then as it results in more collisions, not just with each other, but with the walls of the container, the more collisions will result in a greater pressure. So just based off of the idea of the kinetic molecular theory, we can expect that temperature is proportional, that's what this symbol here means, to the pressure. So if we increase temperature, we increase pressure. Okay, the next idea here is, if I again have a rigid container, that means the volume doesn't change. How does the pressure change when the sample contains more moles of gas? So moles, I'm going to use the symbol N. So if I increase the number of moles of the gas, this will provide more particles in the same volume. And as a result, there's going to be more collisions. And then again, we should get a greater pressure. So here we have moles and pressure also being proportional to each other. Okay, how about a situation where we have a piston? In a piston, you can change the volume. So how will the pressure change when we decrease the volume of a piston? So if I decrease the volume, this is going to have, there's going to be less space now for those particles to interact with each other. And as a result, there will be more collisions. So we're going to consider a lot of this on the basis of collisions with the walls of the container. That's really what we're measuring here, is how often it hits the walls of the container. So this will increase the pressure. So here, the volume is inversely proportional to the pressure. So if I increase the volume, the pressure should decrease. If I decrease the volume, the pressure should increase. Last one, if I have a balloon is something that can be easily compressed or expanded. So kind of similar in a piston sense, but here we're not changing the volume. The volume will change based off of other things. So if I increase the temperature at constant pressure, so meaning like it's still like atmospheric pressure out there, so we're increasing the temperature now. We're going to give more kinetic energy to the particles in the balloon. And as a result, what happens is again, there's more collisions, right? So, but to keep the pressure constant, we're going to need to change the volume. So how do we need to change the volume to keep the pressure constant? Well, we need to decrease the but to keep the pressure from increasing, we need to increase the volume of the balloon. Because the volume of the balloon is inversely proportional to the pressure. So the volume will increase. Because as we increase the volume, the pressure will drop. So here we see that temperature and volume should be proportional. So the only properties that are inversely proportional are volume and pressure. And based off this kinetic molecular theory, now we can look at all the gas laws and already know them based off of this idea. So I like to introduce this first because this gives us a context now to study how these properties relate. So we just talked about all that. So let's look at some of these equations. And if you're going to only understand one equation, you want to know this one, which is pressure volume. The product of pressure and volume is equal to the product of moles times this gas constant R times the temperature in Kelvin. So we can think about two different sets of units. And your textbook talks about both of them. Pressure can be in atmospheres or pascals. If we keep pressure in atmospheres, then volume should be in liters, and the amount should be in moles, and the gas constant should have the units of atmosphere liters per mole Kelvin. And the gas constant works out to be 0.08206. And then if we instead looking at pressure in pascals, the volume needs to be in cubic meters so that the SI units cancel. And then the gas constant takes on the value of 8.314 joules per mole Kelvin because the Pascal times the cubic meters is equivalent to a joule. Now, this equation is known as the ideal gas law. It relates all of the variables to that gas constant R, and the ideal gas law follows all the postulates of the kinetic molecular theory. So under conditions that are high pressure or low temperature, however, meaning like colder, like around 100 Kelvin, the properties will deviate from what this relationship expects. So before we get into that, let's consider the simplest relationships, and then I'm going to plot some of them. So if I have a sample of a gas at 30 degrees Celsius in a piston, and it has an initial pressure of 1.4 atmospheres, and then it's expanded by moving the piston, what is the new pressure of the gas? So we're going to keep it at a constant 30 degrees Celsius, and we're not going to change the amount of the gas. So we can set up a initial final table where I have those four properties, and I grade out the amount and the temperature because those are invariant in this experiment. So this can be seen here with this diagram. We have the piston, and as we expand the piston, meaning we move it up, so we're going to move that pressure up, we know that the volume here now is going to change considerably, and that means that the pressure should decrease because those particles of gas will now have more room to expand. And so as a result, we can expect that the pressure will drop, but by how much? Well, we can use this relationship. We know that the pressure and the volume are inversely proportional to each other. So the product of the pressure and the volume should be equal to some constant. I'm going to use the letter C here. And so we can, since they're going to be equal to some constant, if I take the product of the pressures at two different temperatures, they should be equal to that same constant. So we can set up the relationship as P1 V1 equals P2 V2. And in this sense, we want to rearrange the equation to solve for P2. So I'll rearrange it so that it's P2 equals P1 V1 over V2. And then we just simply plug in the values. Since my volumes are both in milliliters, I don't need to convert to liters here like I would for concentrations. So I always recommend writing it out so you can see how the units cancel. Okay, so it did indeed decrease. So if I go and I want to plot these two variables against each other, so I'll keep pressure here and volume here. Here's my origin. If I have a large pressure, I should have a low volume. If I have a large volume, I should have a low pressure. So you might think that the relationship would be a line between the two. But if you graph this, it ends up being a relationship that looks like this. Okay, so this is the pressure volume relationship. It's inversely proportional. So it's like it's like a plot of 1 over x. All right, so that's Boyle's law. Robert Boyle was also attributed with one of the first chemistry textbooks. You can find it on the Internet Archive. It's called The Skeptical Chemist. I'll look into that. I think it's spelled chemist with a Y. Okay, the next gas law is attributed to Jacques Charles, I think is his first name. He's a French chemist that was interested in the properties of gases, and he flew the first hydrogen balloon over the city of Paris and flew for around 50, 60 kilometers. And along the trip, he brought his brother. He brought a barometer and a thermometer aboard, and so he made some measurements while he was flying above the city, above the countryside, and there was people that were following along the balloon the entire way. And I think they landed it in a field, and some of the farmers in the area were like really freaked out by this, and I think they destroyed it with pitchforks. But this was a huge event. Hundreds of thousands of people were present for that. So Charles, he realized that, if you increase the temperature of a balloon, the volume will increase. I think he had just a closed balloon of hydrogen and realized that hydrogen is very much less dense than the atmospheric air. So you could use it as a means of flight. But let's take a look at this example. I like this one because if you take a balloon and it's at atmospheric pressure, and then you have a dry ice bath where dry ice is really, really cold. That's going to be around negative 80 degrees Celsius. And then, so it's, you initially have the balloon and it's really, really cold, really, really cold. The plastic hopefully doesn't break. And then you heat that balloon up with steam, and steam is very hot. It's around 113 degrees Celsius, a little bit warmer than 100 degrees. How is that volume of the balloon going to change? Is it going to change a lot? Is it going to change a little? You can just use this relationship here to figure it out. So the volume over the temperature should equal a constant, because whenever you have two values that are directly related, the quotient of them equals a constant. Because if I increase the volume, the temperature also needs to increase to keep that constant the same. So we can say that the volume over the temperature will always be the equal to that constant. Doesn't matter what temperature and volume it is. I mean, again, these will change a little bit based off of if we consider that we don't have an ideal gas. But here I have volume and temperature and volume and temperature. So for all these, I guess we could have just assumed we have helium. Helium would be a type of gas that behaves the same under all circumstances. What we're going to do here is solve for the new volume. So I always like to set it up this way, and then I'll rearrange. So I need to multiply both sides by T2. And so I always like to move the value I'm solving for on the left. So here I have V1 times T2 over T1. Now, I left these equal signs here because we need to convert the temperature into Kelvin. So we'll need to add 273 to each of these. We can, I could say 0.15, but since there's no decimal places here, we don't need to do that. Only if there's a decimal do you need the 0.15. Okay, 386. Because of those sig fig rules. Okay, so the initial volume is 193. No, volume 1 liter. And the new temperature is 386. And then the initial temperature was, remember, it was really cold, 193 Kelvin. So the new volume is going to be twice as large, 2 liters. I set that up perfectly, by the way. So no, it's 2 liters. I guess this was 1 liter, so I should put 1.0. There we go. And then we can plot the volume and the temperature against each other. And for 0 volume, we would expect that there's 0 temperature, or like as low as temperatures that we can get, right? So as we increase the temperature, the volume of the balloon will expand. We get a direct relationship. So it's like y equals x. Okay. Pressure and temperature. So in this example, I'm going to have a rigid container, which is kind of what this is representing. A sample of neon is in this container of 1 liter, and it's equilibrated. The container itself is equilibrated in an ice bath, and initially has a pressure of 600 torr. It's then placed into a boiling water bath. Boiling water would be 100 degrees Celsius. So what would the new pressure be? Well, we have to think about, well, how pressure and temperature are related by the kinetic molecular theory. As we increase the temperature, the collisions are going to increase due to the temperature being related to the kinetic energy of those particles. So the pressure and the temperature are directly related. So they'll be equal, their quotient will be equal to a constant. So no matter what pressure and volume we measure, P1 over V1 should be equal to P2 over V2. It should be equal to that same constant, right? So let's set it up so we solve for P2. And we first need to convert these to Kelvin. So 273 and 373. And then the initial pressure is 600 torr. We can keep our answer in torr. It doesn't matter. We only need to convert temperature to Kelvin because these relationships don't work under other temperature scales. So always remember to convert your temperatures to Kelvin. And then P2 will be equal to P1 V2 over V1. Why did I write volume? I think it's when I write the ideal gas law, it's always P times V. I'm always thinking P. Okay. So 600 torr times 373 Kelvin, and we'll divide it by 273 Kelvin. So 820 torr. And then you could convert that to atmospheres or whatever units you'd like. Okay, so if we plot pressure and volume, you will find, not volume, pressure and temperature. We'll find a direct relationship. So the more the temperature, the greater the pressure. All right. One other one is, this is known as Avogadro's law. You don't see this too often in textbooks. Whoa, my document here. Okay. So if we increase the amount of a gas, like say, for example, we're blowing up a balloon. If we put more gas into the balloon, it's going to get larger, right? So the volume and the amount of the gas are going to be equal to a constant. So V1 over N1 will be equal to V2 over N2. The balloon is initially at 3 liters in size, and it's blown up to be 12 liters. Initially, you had 1 mole of a gas, and the pressure is always going to stay at constant atmospheric pressure when you're blowing up a balloon. So we're not going to a different altitude or anything. And then the temperature of the room should be staying the same as well. It might heat up a little bit as you blow more air into the balloon, but that will soon equilibrate. So what we're going to just find here is, and with this one, you don't even really need to do any math. If this is proportional, 3, this should be equal to, this volume here changes by 4-fold. So this needs to be equivalent to 4-fold increase, right? So we can expect it's going to be 4 moles of a gas. So if I want N2 to be by itself, we'll multiply N2 by both sides. And then we'll need to divide by V1 over and then multiply by N1. So N2 will be equal to V2. And then N1 will be on top here. And then V1 down there. You can practice that. So V2 is 12 liters. Just use 2 figs here. 12 liters times 1 mole divided by 3 liters. And that indeed comes out to be 4 moles. So volume and moles are proportional. More moles gas that you have, the larger the volume of the balloon will be. And then we get to the combined gas law. So we can look at the relationship between multiple properties at once. If we keep the amount of the substance the same, we get something called the combined gas law. So we're looking at how pressure, volume, and temperature change. And this is useful for when we have a situation such as a weather balloon where we're going to expect that it's sealed pretty tightly and we're not going to have any gases entering or leaving. But where the balloon changes its altitude, and at different altitudes, we're going to have different temperatures and different pressures. So we want to know how the volume will change of the balloon. And this is a really interesting situation to consider because as we get to higher and higher altitudes, the pressure drops a lot. So the volume should increase a lot. And oftentimes when we release a balloon out into the atmosphere and it keeps going up and up and up, at some point that balloon will pop because it gets so large, and then the plastic stretches out so thin that it pops. So you want to make sure that you have a weather balloon that can withstand those volume changes. The temperature will probably change less quickly than the pressure will. Okay, so how will the volume change here? Well, we'll note that the pressure and the volume, those are inversely related, but both of them are directly related to the temperature. So we can note that the product of the pressure and volume divided by the temperature is equal to a constant. So the combined gas law works out to be P1V1 over T1 is equal to P2V2 over T2. And we want to solve for the new volume. And I already gave us the temperatures here in Kelvin, so we don't need to convert those. We'll start by just rearranging the equation. It's going to look like everything on the left side multiplied by the inverse of what's on the right side that's remaining. So we'll have T2 and P2 here. So I'm just going to group up everything on the top and everything on the bottom. So our pressure is 450. Our initial volume is 600. Our initial temperature is actually on the bottom. So our final temperature is 273. And then our initial temperature is 263. And then our final pressure is 760 millimeters of mercury. So this weather balloon was initially at a high altitude and then it descended. So the pressure increased. So the volume I would expect would actually get smaller here. So let's see what happens. Now here we have a lot of stuff here on the denominator. So you want to include parentheses here. Or you have to divide twice. So it's probably easier to use parentheses. We get that the new volume did indeed get smaller because it descended. It went to 369. I think I would probably round it though to 370 because these are only like 2 sig figs. So 370 milliliters is our new volume. Okay, so the combined gas law, one of my favorite ones to use. It can be tricky rearranging the equation, so just make sure that you don't fumble that and you'll be all right. And then we get to finally the last gas law that I want to talk about today, which is the ideal gas law. And here we can combine all 4 variables, all 4 properties, and relate them to a gas constant known as R. So the ideal gas law is that the idea that the pressure and the volume divided by the N and the temperature are equal to this constant known as R. And this will be the same for all ideal gases. So they'll always be equal to this constant R. So another way of writing this is that PV equals nRT. All right, so let's go and use this to solve this one problem here. Here I have a sample of 0.20 moles of oxygen gas, and it occupies a volume of 4.1 liters at 40 degrees Celsius. Well, first off, I see this is Celsius, so I want to convert this to Kelvin. So we'll add 273. It's 313. And then we want to find the pressure here. So I don't have an initial and a final relationship. I just have like a static a picture here. So pressure volume equals nRT. So we can't use this to look at changes, I don't believe. So what we want to do is solve for pressure. So we'll divide both sides by the volume. And we want to make sure that we use the correct gas constant. So since I have volume here in liters, I'm going to use the 0.08206 value from the beginning. That's in liter atmospheres mole Kelvin. And then the temperature here is 313. And then we need to divide by the volume, 4.1 liters. If you have a graphing calculator, if you are going to use a value like the gas constant a lot, you can store this value as any of these green letters here. So say, for example, you want to store it under R, because that would make sense for the gas constant. Anytime I type R, I get that value. So I like to store a lot of my values like that. So then I don't have to write it each time. So I'll write 0.2 times R times 313 divided by 4.1. See how much easier that is? Okay, 1.25. I'm not going to worry about sig figs here. I mean, I guess I should. 1.25 would be 1.3 atmospheres of pressure. Okay. So that sample is not too much pressure, but a little bit of pressure. So it's important to pay attention to pressure because large pressures can be quite dangerous with gases. Okay, so that's the end of this lesson. We're quite a ways in. We're an hour, 30 minutes in. I have a bunch of these practice problems. I'm going to record these in a separate video here, and you can find these in the modules page. So I recommend working through a couple of these, checking your work, and making sure that you're comfortable with these equations. And then this last one here, let's see. Some of these problems on this last page we won't get until actually the next lesson. Okay, wonderful. Thank you all. Have a good day.